All right. Thank you all so much for your patience. We are going to get started here. Welcome to Astronomy on Tap number 109 in Seattle. Thank you all for making it on this very nice Ballard day. As a reminder, our next Astronomy on Tap will be on August 19th at 7 p.m., the third Wednesday of August, right here at Stoop Ballard. Today, we'll be hearing from Marin on discovering the true nature of dark matter using stellar streams, and from Ishan Ghosh-Coutinho on a study in blue, the case of stellar identity. These will both be very interesting talks, but first, some trivia. As a reminder, please make sure to get your sheet if you don't have one yet, but I'm going to assume everyone does, because I'm going to get started. If you are an astronomer, you can participate, but you can't win prizes. So I'm going to run through them first, and I'm going to read them out loud, and then I'm going to run through them again real quick, and hopefully you can see them. So we're a little washed out because we're outside, but it is still hopefully legible. All right. First, as always as a reminder, Raising A-STEAM is a wonderful program where you can tutor incarcerated youth if you're a UW student, or if you're not, you can donate to help us make that happen. Question 1. Which of the following is not a stellar remnant or compact object? Is it A, a white dwarf, B, a free-floating planet, C, a neutron star, or D, a black hole? These questions also all relate to one of the speaker's talks, at least tangentially, and do vary a bit in difficulty. Question 2. A Hertzsprung-Russell diagram, or an HR diagram, plots which two quantities of stars against each other? Is it A, mass and radius, B, age and metallicity, C, temperature and luminosity, or D, distance and pulsation period? If you've ever taken an astronomy class, you may be familiar with the HR diagram. Question 3. Which element was first discovered as an emission line in the sun's spectrum during a solar eclipse in 1868? Is it A, helium, B, argon, C, neon, or D, sodium? Question 4. Stars of what spectral type are the hottest and therefore appear the most blue? Is it A, B, C, O, or D, G-type stars? I'll give you a hint. The alphabetical order won't help you. Alphabetical order is based on emission lines, not temperature. Question 5. Approximately what percentage of stars of that type are in systems with more than one star? Is it A, 25%, B, 50%, C, 60%, or D, 95%? Question 6. Why is dark matter called dark? A. It absorbs all incoming electromagnetic radiation. B. It is typically colored black or dark gray. C. It does not interact with electromagnetic radiation. Or D. Its influence on ordinary matter is unknown. Why is it called dark matter? And this is, of course, different from the reason dark energy is called dark energy. That would be too easy. Question 7. Which of the following is not a candidate for cold dark matter? A. Axions. B. Primordial black holes. C. Weakly interacting massive particles, or WIMPs. Or D. Neutrinos. All of these are real things, but one of them is not a candidate for cold dark matter. Question 8. Stellar streams are typically formed from what gravitationally bound groups that are more compact than open clusters? A. Globular clusters. C. Closed clusters. C. Stellar associations. Or D. Planetary nebulae. Keep in mind as we go through this that astronomers are really bad at naming things. Question 9. What did Vera C. Rubin, the namesake of the Rubin Observatory, measure to determine the existence of dark matter? Was it A, the orbit of Neptune, B, the rotation curves of galaxies, C, gravitational waves, or D, type 1a supernovae? And finally, question 10. The Navarro-Frank-White, or NFW profile, is commonly used to model the distribution of dark matter in which component of a galaxy? Is it A, the disk, B, the halo, C, the bar, or D, the spiral arm? All right, and now I'm going to go back through them real quick. Normally I don't read them out loud, but I'm going to speed read them this time, and it'll be more fun that way for everyone. Question 1. Which of the following is not a stellar remnant or compact object? A, white dwarf, B, free-floating planet, C, neutron star, or D, black hole? Question 2. A Hertzsprung-Russell or HR diagram plots which two quantities of stars against each other? Or is it A, mass and radius, B, age and metallicity, C, temperature and luminosity, or D, distance and pulsation period? Question 3. Which element was first discovered as an emission line in the sun's spectrum during a solar eclipse in 1868? Is it A, helium, B, argon, C, neon, or D, sodium? Question 4. Stars of what spectral type are hottest and therefore appear the bluest? A, B, C, O, or D, G? And again, all these are real spectral types. You don't have to worry about us trying to trick you. Question 5. Approximately what percentage of this type of star are in systems with more than one star? 25%, B, 50%, C, 60%, or D, 95%? Question 6. Why is dark matter called dark? Is it because A, it absorbs all incoming electromagnetic radiation, B, it is typically colored black or dark gray, C, it does not interact with electromagnetic radiation at all, or D, its influence on ordinary matter is unknown? Say electromagnetic radiation 5 times fast. Question 7. Which of the following is not a candidate for cold dark matter? Is it not A, axions, B, primordial black holes, C, weakly interacting massive particles, or WIMPs, or D, neutrinos? Question 8. Stellar streams are typically formed from what gravitationally bound groups that are more compact than open clusters? Is it A, globular clusters, B, closed clusters, C, stellar associations, or D, planetary nebulae? Question 9. What did Vera C. Rubin measure to determine the existence of dark matter? Was it A, the orbit of Neptune, B, the rotation curves of galaxies, C, gravitational waves, or D, type 1a supernovae? And finally, question 10. The Navarro-Frank-White or NFW profile is commonly used to model the distribution of dark matter in which component of a galaxy? Is it A, the disk, B, the halo, C, the bar, or D, the spiral arm? That is all the questions we have. And so please, if you would, collect your sheets on the table where you got them. Right, I would point the laser, but I don't want to hurt anyone. So if you would, please make sure we get your sheets so that we can grade them, and then give us a few minutes to switch over to the first speaker, and we'll see you soon.
Someone's talking. Alright. Let us get you plugged in.
Yeah, what's the one? I don't really know. I can go out.
Is it captive by conference?
Okay, should I go out? Okay, can I leave this right here? Okay.
Okay, we have to be online. Yeah, totally. So, one of the mics is for the live stream.
Okay.
One of them is for events.
Okay.
This one you just put back in your pocket or flip it off your pants or whatever, and then anywhere near your mouth, and that'll just work. That's a much higher tech way.
Okay.
That one. And do you want a clicker in the hand?
Yes.
You
Yes.
have a USB-A port.
I don't know what that is. Maybe.
No, that's not prepared for that.
I feel like I knew not a lot about it. It was almost incompetent.
Yeah.
First-year grad student in the PhD program. She did her undergrad at Dartmouth, and she is a great member of the community and also in the same research group as me. So she's really cool, and you're in good hands. Take it away.
Thank you, Sam, for that introduction. That was very kind. As he mentioned, I'm here and I want to speak today about what I'm working on in my first year. And it's titled Uncovering Dark Matter in Our Milky Way with Stellar Streams. Okay, so we are going to unpack this title throughout the talk, and we will start with dark matter. So what is dark matter? This is a little history lesson on how we figured out that it exists. So here you're looking at a cartoon version of a galaxy. This is side on. On the far left of the screen, you have the center of the galaxy, and you have the bulge of the galaxy, that big circle. And then in purple, you have the disk of the galaxy. So in our Milky Way, this is where the spiral arms live, this is where the gas lives, this is where the bulk of star formation happens. And then outside of the disk, you have what's called the halo, and there's a bunch of loose stars spread throughout the halo. So if this diagram were our Milky Way galaxy, that's where we would be, that's where the sun would be. Somewhere in the disk, far out from the center, but in the densest region of the galaxy. So in 1970, we have two famous astronomers, Vera Rubin and Kent Ford, who sought to measure the rotation curve of M31. M31 is the nearest, largest galaxy to the Milky Way, also known as Andromeda Galaxy. And the rotation curve is a measure of how fast the galaxy is spinning as a function of distance from the center of the galaxy. So the expectation is that the rotation curve of M31 would look something like this, that the galaxy would be spinning much faster, closer to the center, and would slow down in its rotation as you left the center of the galaxy. And this is because of that equation I put up there, where the velocity of the galaxy is proportional to the square root of the mass over the radius. So if there's more mass in a given radius, which is true for the center where the bulge and the disk is, the velocity should be higher. But that is not what they found. This is the reality of what they found. They found that the rotation curve actually flattens, and that the galaxy is spinning just as fast in the outer regions as it is towards the center. There's a little peak in the very center, but regardless, strong deviation from what they would have expected. So other than that equation being wrong, which I think it was Newton who figured that out, which would be a very big claim, the only other explanation for what Rubin and Ford saw was that there must be missing matter. These high velocities in the outer regions of the galaxy means there is matter that we cannot see that is driving the rotation of this galaxy. So if this is the galaxy as Rubin and Ford saw it, and as we see it, this is what the galaxy actually looks like. Sorry, the lighting is kind of tough, but it is enclosed in a giant halo of dark matter, and this is true of every galaxy. Every galaxy sits in this large dark matter halo. So dark matter is just describing this phenomena, and the core meaning, I guess, is in the name. So dark meaning that it's invisible, which is why we didn't see it, which is why we didn't expect the rotation curve to look that way, and matter because it does have mass. Further, dark matter is more than 5 times more abundant than visible matter, which is just a cool factoid and also very motivating for why we should study it, because, again, like looking up in the sky, everything you see, there is more than 5 times of that available in dark matter. Another key point is that dark matter, it does not interact electromagnetically. This is just a fancy way of saying it's invisible. It does not emit or absorb photons, but it does interact gravitationally. This is because it is massive. So this is very important because dark matter dictates the way galaxies form and grow. So in this little cartoon diagram, we have the dark matter clump in the center, and the gravity of the dark matter can pull in things that we can see, like gas and dust, which are the seeds of star formation. So you need those two things to form stars. Even bigger dark matter clumps can pull in full stars themselves, and even bigger than that can pull in full galaxies. So the dark matter is very critical in determining how things form and where things form. Okay, so the galaxies therefore trace the dark matter. Where the galaxies exist is also a place of high density dark matter. So here we have a galaxy cluster, and we have a void. And this is the underlying dark matter distribution of that region. So this image that you guys are looking at is what's called a cosmological simulation. It's a big chunk of the universe and of the dark matter distribution within it. Again, hard to see, but kind of looks like a spider web. Important things to note here. Yeah, so the galaxies are coincidental with the highest density regions of dark matter. And there's also these things called voids, which are regions of no dark matter, or very low density dark matter, and therefore also regions of no galaxies, so regions of pure empty space. This is a clip I took from a YouTube video to kind of give you a sense of scale. So if that was our Milky Way galaxy, this is us zooming out until we get to the size of the simulation I just showed, the cosmic web. Cool. So that is a very zoomed out map of the universe, a very computationally intensive simulation. Okay, so the galaxies trace the dark matter, and in turn, the dark matter dictates where the galaxies form. So this is a cool video I like to show of a galaxy forming in a dark matter halo throughout cosmic time. Thank you, Sam. Cool, so this is, dang, I hope you guys can see. This is the start of the evolution of the universe. The dark matter is very diffuse, and it slowly condenses and collapses under its own gravity to form higher and higher density regions. So this is a simulation of one single galaxy. So in a few seconds, you're going to start to see these little high density regions collapse together and continue to form the one central galaxy. We'll give it a few more seconds. Okay, so you can definitely see the high density regions emerging, and there we go. In the center, that green portion, it looks green to me, is the galaxy that is forming. So again, the dark matter dictating where this galaxy forms and feeding in all of the ingredients for it to grow along its filaments. I think this is good on this video, Sam, if you don't mind pausing.
Hold on.
Ooh.
Maybe the video is over. Aha!
Cool. Okay, moving on to the next part of my title, which is the Milky Way. So just a recap of what we talked about. We know dark matter exists. Thank you to Vera Rubin and Kent Ford for their rotation curve analysis. And we know that every galaxy lies within a dark matter halo, and that's how it was able to form. So the next question we're asking is, what does dark matter look like on subgalactic scales, for example, like within our own Milky Way? So here are kind of the two main theories that emerged after dark matter was discovered, the hot and cold dark matter theory. So to start with the hot dark matter theory, this theory is the theory that the fundamental particle of dark matter is very light. It travels super fast, close to the speed of light, and because these particles are very light and traveling very fast, it's hard for small structures to form. They need a lot of mass in order to keep these particles gravitationally bound without flitting away because they are so light. So you'll notice in the left-hand simulation, there's much fewer clumps because it takes a really big clump to keep these particles bound. Yes, less small-scale structure. This theory also supports the theory of top-down formation, which is the theory that the universe started as one giant pancake of matter, and everything that we see now has fragmented off of this pancake. So the pancake was at the start, and then we had superclusters of galaxies that broke off. Those superclusters broke off into clusters of galaxies, and those clusters broke off into the individual galaxies we see today. On the other hand, the cold dark matter theory is the theory that the fundamental particle is much heavier. This means that much smaller clumps are able to form because the fundamental particle is heavier, it has more mass, more gravity, it can hold together in clumps better. And this theory supports the idea of hierarchical formation or bottom-up formation. So this is the theory that everything we see in the universe started very small and combined and merged to form larger and larger structures. So in the early universe, we had small galaxies. They have combined at later times to form clusters. Those clusters have combined at later times to form superclusters. So as it turns out, at this point in time, pretty much hot dark matter has been all but completely eliminated, and cold dark matter is the most popular theory that we have today. And this is because it matches what we actually see at large scale. So in the early universe, we actually see galaxies before we see clusters and before we see superclusters. So this means that the little structures existed before, which means that they must have combined to form the clusters and the superclusters we see today. So you might be wondering, okay, how can you see that far back in time? This is a question I had before starting getting involved in astronomy, but the observations we have are actually so distant that the time it takes the photons to arrive at our telescope, we're seeing galaxies from the early universe. I think, yes, I have included a little image of an early galaxy, so this is kind of all they are, these little smudges, but this is what it's taken to confirm or provide more evidence that this cold dark matter theory is correct at the large galactic scale. But this section is about the Milky Way fundamentally, so we want to ask, what does dark matter look like at smaller scales within the Milky Way itself? So a key prediction of cold dark matter, if it is true, is the existence of what's called dark subhalos. So here we have an image of the Milky Way galaxy. Again, it's sitting in a large dark matter halo, and this dark matter halo has what's called subhalos, or smaller clumps. Some of these clumps are really massive, and they have dwarf galaxies within them, but some of these clumps are too small to have enough gravity to host anything, and they remain completely dark. They don't have any visible component within them. The cold dark matter theory also makes some predictions for the abundance, so how many of these little clumps should we expect to see, and the density of these subhalos, like how dense they are. So going forward, we want to figure out, okay, cold dark matter matches what we see at these big scales, does it match as well at these small scales, or do we need an alternative theory? So how do we figure out if they exist if we can't see them, and further, how do we figure out if the properties, the abundance and the density, match what is theorized from cold dark matter? This leads me to the final term of my title, called stellar streams. Okay, so what is a stellar stream? So we're going to pause on the last question of how we're going to figure that out. The answer will be stellar stream, but first we're going to understand stellar streams. So stellar streams they were once a dwarf galaxy and a globular cluster that fell into the Milky Way. They became gravitationally bound to the Milky Way, and the gravity of the Milky Way shredded these structures into long, thin lines. So you can see in the left, we have that kind of clump feature that is a dwarf galaxy, and you can see it has these long tidal tails extending from the front and the back. And one day, the entire dwarf galaxy will completely dissolve, and it will be one thin, long stellar stream. On the right is an artist's rendition of the galaxy, and there are little colorful streams orbiting all around. Okay, this is a simulation by Videep Reddy, who's an undergrad in my group, and this is of a stellar stream disrupting. You could see it continues to get longer and longer and thinner and thinner. Okay, so stellar streams, by nature, they're very thin. They've been shredded, so they're these thin structures on the sky, and they have consistent velocities. All of their stars are pretty much moving in the same direction of the orbit of the initial dwarf galaxy or globular cluster that formed them. This makes them very sensitive to gravitational perturbations. Gravitational perturbations is kind of the fancy language we use, but what that means is when an object comes close enough to use its gravity to exert a force on the stars in the stream, we are able to notice that because the stream is so thin that if a star is displaced, we can see it. If a star's velocity suddenly changes direction, it's very obvious because the bulk of the stars in the stream are all moving in the same direction. So anything that changes direction is a clear signature that there was some type of impact in its history. I.e., if a dark subhalo, for example, comes close to a stream, we expect to see evidence of that in the stream structure. We expect to be able to figure that out. this is the end, but this will start over here. Okay, so this is a stellar stream that's forming. It's getting longer and longer as time goes on. In about 25 million years from the present day, a subhalo will enter that will appear as like a little yellow circle. There it is. It will pass in front of the stream and it will perturb the stream or push some of the stars out of alignment, and it will result in a signature that we can actually see. So here are some screenshots from that simulation. The top left, you have before the encounter. In the middle, you have the subhalo coming in, and at the end, you have what's left after the subhalo has passed by. So that is a signature that we can clearly see, and we can backtrace to figure out the properties of the subhalo that caused it. So here are two examples of real streams where we see these types of perturbations in their structure. So on the top we have GD1, and GD1 has two well-studied features, the spur and the gap. So the spur is that like extended section of stars, and the gap is that little underdensity at about -20. Don't worry about the axes in these plots, just know that these are all stars, and this is them in spatial coordinates, and they're moving across the sky. So two main features in GD1, and then in the bottom we have Atlas Alika Uma stream, the AAU stream, and this stream has a well-studied kink feature, this kind of ripple in its structure over there on the left. So we see examples of these streams and these perturbations in real observations. Here is a diagram of the full Milky Way stream census. So we have over 100 of these objects known, and pretty much all of them have these perturbations in them. They pretty much all deviate from these thin structures, which is exciting because it means many opportunities to study their features. Okay, so given these streams' very messy structures, how do we then constrain the properties of these dark subhalos, and furthermore, do the subhalos match the predictions made by the cold dark matter theory? So how do we do this backward analysis? This is the technical answer, and this kind of sums up what I have been working on all year, but it is called simulation-based inference. So it is this very cool machine learning technique where you take a large batch of simulations. So we make simulations of these stellar streams, and we throw all different types of subhalos at them. Massive ones, super dense ones, fast ones, slow ones, coming from the top, coming from the bottom, all different simulations. And then we ask a neural network to learn the parameters. So we feed them this stream, it takes a guess, okay, I think the subhalo is this massive and this dense and moving this fast. We then reveal, or we don't, it reveals to itself the true answer, learns from that, adapts, and keeps going until it is fully trained and pretty confident in being able to make an accurate guess. And then we give it real data, and we ask, okay, after all your training, what is the mass, radius, velocity of the subhalo that perturbed this real stream? And it gives us a posterior distribution, a probability of the properties, which is very cool. So really cool technique. It's taken me a while to learn, and I'm still learning, but learns a relationship between stream structure and the properties of the dark subhalos. Okay, so assuming, yes, so specifically, I have been working on the AAU stream, the Atlas Alika Uma stream, the one I showed earlier with that kink in it. I've been working specifically on that and trying to figure out what are the properties of the dark subhalo that caused that kink, assuming it was a dark subhalo that caused that kink. So actually, as of like very recently, I have some preliminary results. This is just results for the mass and the radius. These are on log scale, this plot. This is a pretty big area of parameter space, but we kind of think that if a subhalo perturbed the AAU stream, it would have a mass in that dark blue region and a radius in that dark blue region, which is exciting progress. However, an important caveat, subhalos are not the only cause of stream perturbation. This is a big thorn in my side. So there are many visible things that also can perturb streams. We have the bar, which is this vertical structure that goes through the center of the galaxy. We have giant molecular clouds, these just big clouds of gas, and we have satellite galaxies. All of these objects can cause things like a kink, cause things like a gap, cause things like a spur in the stream structure. And this is specifically, these things are specifically relevant at smaller galactocentric distances, which means closer to the center of the galaxy, where the majority of these things exist, not out in the halo, if you remember the first cartoon. But the gravitational wake of the Milky Way itself can also cause stream perturbation. So even out in the halo, the bulk mass of the Milky Way as it rotates, that gravity exerted on the streams by that bulk mass can also cause kinks and spurs and gaps in the stellar streams. And this is very relevant at all galactocentric distances. So way out in the halo, way close to the close to the disk. In Arpit, Aurora, a postdoc who I work with, recently published work demonstrating that this is the case. So these are all simulations from run without dark subhalos, but run in a very realistic Milky Way. And all of these streams have some type of messy structure, some type of kink or gap, which is important because we don't want to falsely attribute these to the dark matter subhalos. We want to make sure that we are separating what was caused from the Milky Way, what was caused from the bar, and what was caused from a subhalo. So in order to isolate the dark subhalo perturbations from the perturbations caused from the bulk mass of the Milky Way, we believe the way forward is to just get a super large sample of these stellar streams and run similar SBI analyses on all of them. So currently working on AAU, hoping to expand this analysis to hundreds of streams. Luckily, we have a lot of very exciting surveys that are coming up that we are hoping to provide this large population that's needed. We have LSST that actually recently started a week or two ago. This is covering the entire sky of the southern hemisphere over 10 years, and it is covering in the optical wavelength regime, so the visible wavelength. We have the Roman telescope that's coming on soon that is covering more select regions of the sky in the near infrared, so in these redder wavelengths. Combining all the wavelengths will be very powerful, and Euclid similarly will be observing in the near infrared wavelength regime. Okay, that is all I have, but want to do a quick recap. Dark matter exists. It's invisible, 5 times more abundant than visible matter, and every galaxy we see lives inside a dark matter halo. The cold dark matter theory is the most popular theory we have, and it agrees with the observations of the universe on large scales. However, on small scales, like within the Milky Way, cold dark matter predicts the existence of these dark subhalos, which don't have a visible component because they're too small. They don't have enough gravity to pull in anything visible, so we can't see them. We need another method. Stellar streams can help us find these dark subhalos, and interactions with them are reflected in their structure in the form of like a kink or a gap or a spur. But dark subhalos aren't the only thing that can perturb these stellar streams. The visible structures we talked about, these satellite galaxies, and the Milky Way itself can cause perturbations in stellar streams. So to solve this, we need a large populations of stellar streams to isolate the perturbations that were just caused by the dark subhalo and answer all of our burning questions about whether or not the cold dark matter theory is correct. Thank you so much. Cool. I think we're doing questions now, so if anyone has questions. Yes. Oh. Okay, am I running questions? Yes.
That's great. Thanks so much.
Yeah.
Thanks for the awesome talk.
Yeah.
So, if all this dark matter exists, right, and it like gets sucked up by black holes, do you think we'd see those black holes grow much faster than what we'd see by the normal mass of positive?
Ooh. Interesting question that I haven't thought much about. I think that because dark matter has existed since, the beginning of the universe, it's always been there, that if the black holes were going to be sucking up the dark matter at a faster rate, we would already be able to observe that. So I think that the dark matter is very plentiful and that the black holes are not going to be growing any faster than they have been growing as of late. Hopefully that answers your question. Other questions? Yes.
The evolution of dark matter, was it in concert with regular matter, or is there a theory which came first between the two?
They all coexisted together at the start. Oh, yes. The question was, is there a theory of how dark matter evolved with visible matter? Did one come first? The answer is that they were all there at the beginning of the universe, and they've all evolved like together, I guess. Yes, but the standard model particles, the hydrogen, was all there at the beginning, with the dark matter particle that is still unknown. Yes.
Why would a larger population of stellar streams help isolate the perturbations?
Great question. So the hope is that yes. Why would a large population of stellar streams help us isolate the dark subhalo perturbation? So the idea is that with a large population of stellar streams, we can identify trends. Specifically with what I was talking about with the Milky Way causing those perturbations, we want to find stellar streams in the outer halo where they're more protected from the visible structures, the satellite galaxies in the bar. And if we can isolate those, we just have to worry about the Milky Way mass. And we're hoping to see, we do already have initial evidence of some trends of how those perturbations scale with distance, like less perturbations the farther out you go. So we're hoping with a robust population to kind of identify that trend, and then deviations from that trend we can confidently attribute to dark subhalos. Yes, yes.
Is there a possibility, if you subscribe to the Big Bang model, I'm being loud so everyone can hear me, if you subscribe to the Big Bang model, then is it possible that the Big Bang was all the matter and it expanded into the dark matter that might have been there before the Big Bang? In other words, was the dark matter the universe that it expanded into?
Great question. Something I have not thought much about. I don't think that is the scientific consensus. If any other astronomers want to weigh in, I think that is not the consensus, but I don't actually know why. But yeah, I mean, the simulation I showed, the dark matter was much more diffuse at the early universe, which is consistent with the early universe being a much hotter, denser place, and then it cools and collapses. But we input the initial conditions into that simulation. Very just interesting thought. Yeah, I don't think that is been investigated. Steven.
Are those like in like specific time moves? Like after the perturbation happens, like something fast doesn't snap back into a normal straight shape, or it's in like forever conserved until another gravitational thing goes.
Yeah. The question was those perturbations, like the kinks and stuff, are they forever? Is that like a specific snapshot in time, or do they ever snap back? The answer is, I'm going to say no. It's probably more nuanced than that, but once the stars kind of get pushed out of alignment, because they're just out there in space, they'll keep traveling in the direction they're traveling. If anything, the perturbations will get more pronounced over time, and the streams will just continue to get messier over time. Yeah. Yes.
Second question. Between networks like the output of these games, like your standard distributions, so I'm just wondering, like, getting the standard distributions, right? Are you seeing like prior distributions to govern like how the network works, or are you just seeing like the strings themselves as like inputs and then letting the prior can learn along with this? Because then that can like draw and like parameters away from like what they're actually supposed to be if they're not defining it properly, right?
Great machine learning question. Glad you're here, and I need practice with this. The question was like, are we using a prior in the neural network? The answer is yes. So all of the simulations I have, all of the subhalos that are thrown at them or that they're simulated with, the properties of that subhalo are drawn from defined priors beforehand. Yeah. Yeah, I don't think. We are exploring other sequential methods that I think would redefine the prior during training, but not currently doing that. Yes.
Was the evidence for the That is a good question. I think that Webb surely bolstered the evidence in favor of cold dark matter at large scales, but cold dark matter has definitely been around and widely accepted. I want to say since like the early 2000s. So I focused on kind of that structural formation, but there are multiple different lines of evidence that have supported the cold dark matter theory on those larger scales. Yeah. Sorry, I didn't repeat the question. But yes.
This came up in trivia, but I know there are subatomic units like that.
Oh yeah.
For this, I guess if your posterior distribution looked a certain way, would that inform possibly which subatomic units fit the model test?
100%, yes. So the different candidates have different predictions for the abundance and the density. Those are kind of the two main things I'm thinking about right now of the dark subhalos on small scales. So yes, cold dark matter has a very specific prescription, but if it was axion dark matter, for example, the abundance we would expect to see and the density we would expect to see would look different. So once we have isolated what we believe is a subhalo perturbation, looking at the density and looking at, okay, how many subhalo perturbations are we seeing? Are we seeing only one in a population of, 1,000 streams, or are we seeing 100 in 1,000 streams? That kind of information will help us distinguish from the astronomy side which candidate. But there are plenty of physicists who are working on the particle side of dark matter using lab experiments as well and coming at it from that direction. Yeah. Yes.
You said that depending on the size of the dark matter pockets, it can interact with larger and larger things. Have we seen any dark matter pockets large enough to alter the trajectory of galaxies, like whole galaxies or anything like that?
Yes. I mean, so I guess, yes. So that's a tricky question, a nuanced question, I would say. On the whole, the universe is expanding. So everything is supposed to be moving away from each other. Sorry, I have been doing a horrible job of repeating the question. The question was, do we have an instance where we have seen dark matter attract one galaxy to another? Is that fair?
Yeah, just like move galaxies away from where we expect them.
Move galaxies away from where we expect them, yes. The example that's coming to mind, right, if the baseline expectation is that the universe is expanding, galaxies should be moving farther away from each other. The M31 galaxy, the one I mentioned in the very beginning, Andromeda, is actually moving closer to us. And that is perhaps unexpected, and that is because we are in a gravitational relationship with M31 due to both our visible mass being attractive and our dark matter halos being attractive. So yeah, I would say that is deviated from what we would expect in the absence of dark matter. One more question, says Sam. Yes. Okay. That is such a great question and something I'm very. Ooh. The question is, like, we have our Milky Way, we're studying the subhalo population of the Milky Way. Do we have the resolution to study the subhalo population of other galaxies farther and farther away? And can we say something about how the subhalos evolve with how galaxies evolve? And the short answer is no, we can't really do this for other galaxies. We've just started to be able to identify streams around other galaxies, but not at the resolution needed to identify any perturbations or things like that. So at this point, just kind of using the Milky Way as a test bed and understanding perhaps about spiral galaxies and this type, but can't generalize to other types of galaxies. Ooh. Do I see technology getting to that point? I don't know. I feel like the technology is pretty good and we can't do it now. So pessimistically, maybe not, but anything is possible. Maybe we send a telescope on a spaceship into space. Okay, that is my time, I believe. Thank you.
Good work.
Thank you.
All right, thank you, Ella. Let's give Ella another round of applause. All right, at this time, we're going to take a quick 5 to 10 minute break to switch over to our next speaker, do our trivia stuff, all that good stuff. Now would be a great time to get some more beer, patronize this wonderful establishment, go to the bathroom if you have to. See you soon.
Can you tell me?
All right, hello everyone. Welcome back to Astronomy on Tap. I hope you all have enjoyed your brief intermission, and I'm sure people will continue to trickle in as I go over the trivia answers. Woo! So, question 1 was, which of the following is not a stellar remnant or compact object? The answer is a free-floating planet. All the others are the end state of a star. Planets are just planets. Question 2, a Hertzsprung-Russell diagram puts which two quantities of stars against each other? It is temperature versus luminosity. Tells you a lot of good stuff about stars. Question 3, the element that was first discovered as an emission line during a solar eclipse was helium. And you can tell this because it is called helium, like Helios, which is the adjective for the sun, and that is why it's called helium. Even though nowadays you mostly associate it with water, but it was discovered in the sun. Question 4. Stars of what spectral type are the hottest? This is the O spectral type. They are the hottest and tend to be the largest. And the letters are, well, the letters will be talked about later, so you'll find out about that. Question 5. Approximately what percentage of stars of that type, which is O type, are in systems with more than one star? This is a very high amount. This is 95% according to my sources.
I disagree. We'll talk about it.
Ishan disagrees, and we'll fight about it later behind the dumpsters. Question 6. Why is dark matter called dark? This is because it does not interact at all with electromagnetic radiation. It's called dark because it does not emit radiation, it does not absorb radiation. We cannot see it via electromagnetic radiation, so it is very hard to see, which is why it's called dark. It only interacts via gravity. Question 7. Which of the following is not a candidate for cold dark matter? This is neutrinos. Neutrinos, we're pretty familiar with them. We know what they are. They're not dark matter. The other ones could be, though. Fun fact, axions are named after a cleaning product that's very popular in Latin America. Question 8. I said question 8. Thank you. Stellar streams are typically formed from what gravitationally bound groups that are more compact than open clusters? These are globular clusters. Stellar streams also can be formed from dwarf galaxies, but globular clusters are a very popular way to form them. Closed clusters, unfortunately, don't exist. Sorry. Whoops. Question 9. Vera Rubin measured the rotation curves of galaxies to prove dark matter, as we saw in Ella's talk. And question 10. The Navarro-Frank-White, or NFW profile, is commonly used to model the distribution of dark matter in the halo of a galaxy. It measures the density. And so those are the answers. And now, the moment you've all been waiting for. The winning teams. So, there are 3 teams that got 8 out of 10. And 2 teams that got 9 out of 10. So, if you are one of the winning teams, you should celebrate when I call your name. And then at the end of the talks, at the end of the event, you should come up and find me and claim your prize, which is some manner of astronomy paraphernalia. So, the first team with 8 points is Team Singularity. Good job. Next up with 8 points is Team Regolith. Big moon fans. And last team with 8 points is Team Not in Florida. That's correct, this is Seattle, Washington. And the 2 teams with 9 points are Team Stan D. Nice. And finally, Team Spaghetti. Congratulations to our winning teams, and I will see you at the end of the show. Now, if you give me approximately 2 minutes, we're going to switch over to the next slides and get started. Okay, thank you. right. It is now my great pleasure to introduce for our second talk. This is A Study in Blue, a case of stellar identity. This talk will be presented by the wonderful Ishan, aka Isha Ghosh-Coutinho, who was an undergrad at the University of Washington and then a postbac at the University of Washington, and is now a grad student at KU Leuven in Belgium, and has done some really cool work with stars. So give it up.
All right, okay, this works. Cool. So hi, yeah, I'm Ishan or Isha, and today we're going to be talking about a little mysterious star. So before that, just some background about me. As Sam said, I was a undergrad and then postbac at the Department of Astronomy at UW. I'm currently at the Institute for Sterrenkunde, which is literally translates to the Institute for Star Studies or Astronomy at KU Leuven, which is in Belgium. And the third thing you should know about me is that I love stars. I love all kinds of stars. I love bubbling red supergiants. I love disk-forming hot blue stars. I love stars that go boom and pulsate in the night. I love open clusters of stars. I like interacting binaries that collide and explode. I like surveys of stars that cover the entire night sky. And the reason I'm back at UW this summer is I'm particularly excited to work on a current survey that's just started a couple weeks ago, named after Dr. Vera C. Rubin, the Vera C. Rubin's Observatory's Legacy Survey of Space and Time, that's going to create a 10-year movie of the night sky. The lovely folks at Rubin, I think, personally hate me because they like making my life hard. They've caused a really big problem. There are too many stars. This is a revolutionary point that no one has, in the history of AOT has ever made before. A couple years back, this is Professor James Davenport, my former advisor at UW, who made the point that there are too many stars because our catalogs seem to keep growing. I'm not going to rehash his entire talk. It's on his YouTube channel. It's a great talk. But I'm going to steal one slide from it because it's a very good slide. How does a laser work? Okay, cool. So starting in the 1800s, we have, this is on this axis, you have years. On this axis, you have orders of magnitude. So this is about 10 to the fourth. Astronomers love magnitude, so 10 times 10, like 4 times. And so this is where we were in the 1800s. We go up 1 order of magnitude for like the rest of the 1850s to the 1950s. And then something happens in the 2000s. Other than me being born, something else happened. Does anyone have a guess what happened in the 2000s that would cause this giant jump in catalog size? Not Hubble. That was actually before that. Does anyone remember when computers became really good? I don't. I was a baby. But apparently computers got really good, and this correlates with this giant jump in catalog size. And then in the right as I was entering the field, Gaia DR3, the third data release of the Gaia mission, came out in the early 20s. And that jumped us another order of magnitude. So now we're at like 10 to the 9th. And this is a bit of a problem. Because now we have the Vera C. Rubin Observatory that's going to jump us past 10 to the 10. The Vera C. Rubin Observatory, over its 10 years, is going to observe more stars than there are people on Earth. It's going to be well over 10 billion stars. And so this is the Gaia mission. This is 2 billion stars. This is already a lot. The star I want to talk about today is, I think it's over there. That's the star I want to talk about today. That's like less than a pixel on this image. So there are way too many stars. We can't really hope to classify or work with each of these stars individually. There are literally not enough people on the planet to work with each of these stars individually. I'm zooming in on the star I want to talk about just so you can get a better idea. It's going to be that little dot there. We're going to get back to it. But first I want to talk about how we can approach working with an individual star. We can kind of approach it like detectives, but for space, where detectives might use fingerprints and DNA to like try to find a mysterious suspect and use tools like a magnifying glass or John Watson. Astronomers instead have to use different clues and different tools. So the clues we get are things like the color of a star. We can give the size of a star, which is a little bit of an oversimplification. Size basically is me just bundling a bunch of stuff together, like a star's radius, a star's mass, or how much stuff is in a star, a star's luminosity, or how bright it is, which is something we can actually directly observe, and a star's surface gravity, which is also something we can directly observe, but that'll come back maybe towards the end. The last third big thing, apart from color and size, is composition. So what a star's, mostly its atmosphere, is made out of. Then there are also a bunch of secondary information, like a star's location. Where is it in the Milky Way or universe? How far away is it from us? How is it moving through the night sky? How is it behaving over time? The tools we have a few different ones. The first one is called photometry. Photo is, I think, Greek for light. And it's literally that. It's measuring light. So we're measuring the color for a star. We're measuring how bright it is. That's all photometry. Then we have astrometry, which is measuring a star's position, its position over time, how far away it is, where all of that is astrometry. And then the last one is spectroscopy, which I'm going to explain, and that's the study of spectra. It's the study of rainbows, like literally like the rainbows up there. And the tools we primarily use to do that are telescopes, and we have two types of telescopes broadly. We have ground-based observatories, and we have space-based observatories. So, spectroscopy. Spectroscopy is the science of turning a single beam of white light and splitting it into its component colors, and then using that colors to find out more about the object or material you're studying. So every element has this kind of very unique fingerprint, this very specific colors in which it glows. So you have sodium up here, which has these very specific colors it's going to glow in. You have hydrogen here that's going to have these very specific colors it's going to glow in. And some of these lines overlap, but for the most part, every element is going to have individual lines we can identify it by. When we do this to a star with a modern telescope, you end up getting a plot on your computer that looks a bit like this, where if a star had perfectly the same amount of light in every single wavelength, in every single color, this would be a flat line. But because of these elements being present, some lines are you're going to get these absorption lines where the elements have eaten some of the color. So you get these like missing lines in your spectrum. And each of these correlates to a specific color. And the depth of these lines shows you how strong that particular element's effect is. The person who really put this into practice was Annie Jump Cannon, who was a member of the Harvard computing group in the turn of the 20th century. The reason Annie Jump Cannon, by all rights, is a scientist and is an amazing scientist and is foundational to the field of stellar astrophysics. But the reason she was called the computer at the time is because the patriarchy existed and still exists, and women weren't allowed to be scientists at Harvard. They were instead called computers, but they did fantastic work. The Harvard computing group, led by Annie Jump Cannon largely, did the work of sorting the spectra into the order that we astronomers use today, starting with the simplest lines on the top that mostly have the signatures of hydrogen and helium, to more complex ones going down all the way to the bottom, where you can also see the spectrum has shifted from being the peak being over here on the left to the peak being on the right, and having these giant chunks, which are mostly thanks to a molecule called titanium oxide. And you can kind of see this progression, and this progression resulted in categories that Annie Jump Cannon reorganized the old alphabetical system into, so that we have O first, which is all the hottest stars with the simplest lines, B, A, F, G, K, M to the coldest stars that have the most complex lines and have those molecular lines as well. So not just atomic lines, but molecules. The acronym that I like to use for this is old bread and food gets kind of moldy. We have competing acronyms, but this is the one I'm going to use for now. This is just how you should remember the category. So O is the hottest, bluest, with the simplest lines. Go down, M is the coldest, reddest, and has the most complex lines. We can kind of put this into practice on something called the HR diagram, the Hertzsprung-Russell diagram. Sam informed me that the Hertzsprung is misspelled here, but we're just going to ignore that. So over here, you can see that we have the blue stars on this end, the red stars on this end. So the O stars are over here, M stars are over here. We've added another dimension, though, where we've added luminosity. And what luminosity is really a proxy for, given that if you make some assumptions that I'm going to hand wave, for any given temperature, luminosity is a direct approximation for size. So you got small stars down here and big stars up here. So the higher up you go on the y-axis, the bigger your stars. The further you go this way, the redder the stars. The further this way, the bluer the stars. So that also tells us another thing, which is temperature and color are directly related. So we can substitute temperature for color. We can substitute luminosity for size. Big go this way, blue goes this way. And another person I'm going to shout out is Cecilia Payne-Gaposchkin, who was an astronomer who 101 years ago published her PhD thesis that went against the prior wisdom of the field, that thought that stars, especially the sun, would be made out of the same elemental amounts as the Earth was. And Cecilia Payne-Gaposchkin used the work of Annie Jump Cannon and other people at other women at Harvard to an added quantum physics, and was able to prove that stars are mostly made out of two things, hydrogen and helium. Stars spend most of their lifetime fusing hydrogen into helium, so those are going to be the two most common elements we see. That's also why those are the two lines that you're going to see across all the spectra, and why O and B stars primarily just have hydrogen and helium lines. But this continues to be, even 101 years later, probably one of the most important PhD theses written in stellar astrophysics. But that's all the background I have. So let's go back to the star I want to talk about, because this star, is one of 2 billion stars in the Gaia mission. It was not classified by hand initially. It was classified by machine learning. And when I say it was classified by machine learning, I'm not talking about large language models. No one uploaded this into Claude. No one uploaded this into ChatGPT. Hopefully, that's not how scientists do science. I'm going to ignore neural networks for now. But broadly speaking, when you're reading a scientific paper, most of the machine learning you're going to come across is something called machine learning regression or machine learning classification. And what that is, very simply put, is a number predictor or a sorted into category machine. In this case, it's the latter. A machine learning algorithm developed by the Gaia mission team was used to sort the stars observed by the Gaia Space Telescope into different categories to predict what kind of stars they would be. So the data was taken by Gaia, fed through the Gaia mission team's machine learning classifier, and it said it's a white dwarf with 99.9% probability. Whenever you see 99.9% sure, that's a very suspicious number. I'm actually going to spend the next few minutes disproving this machine learning classifier, because I don't think this star is a white dwarf. Here are clues so far. We know the star is blue. We know that much from the Gaia mission. It is definitely blue. That's in line with a white dwarf. We know that it's hot. That's also in line with a white dwarf. Those are two of our clues. We know the color, and we know the temperature. We don't know anything about the star's size, though, yet. We do know something about its location, because Gaia is very good at astrometry. So we do know that this star is right about there in something called the Small Magellanic Cloud. This is not a great picture on this screen, but this is an image taken from Australia. You can see the southern lights over here. You can see the disk of the Milky Way rising above the photographer. You can see the Small Magellanic Cloud there, and its cousin, the Large Magellanic Cloud, right above it. These are not visible in the Northern Hemisphere. If you want to go stargazing to see them, you'd have to travel to Australia, Southern Africa, or South America. White dwarfs are the end state of sun-like stars evolution. That's what the sun will turn into in about, well, some billion years. And they kind of are these really compact Earth-sized compact objects, the remnants of main sequence stars. And they're kind of down here on the HR diagram. They're very hot, they're very blue, but they're very small. In fact, they're so small and they're so dim that for a white dwarf of the brightness we observe this star at, it would have to exist within about 4,000, 5,000 light years of Earth. What's weird is we observe this star right on top of the Small Magellanic Cloud. Not only, which is, okay, that could be a coincidence. Maybe it's a star that's in front of the Small Magellanic Cloud, but just 4,000 light years away. But it's also moving with the Small Magellanic Cloud, and that's what this diagram is. This is showing how much the star is moving in one dimension and how much is moving in the other dimension across the night sky. All these gray points are other stars in the Small Magellanic Cloud, and our star is right on top of them. So this star is where the Small Magellanic Cloud would be in line of sight. This star is moving with the other stars with the Small Magellanic Cloud. But if Gaia is right and it's a white dwarf, it has to be significantly closer to us than the Small Magellanic Cloud is. To get a sense of scale of where the Small Magellanic Cloud is, I just grabbed this picture of Google of the local neighborhood. And this is, again, to my point of there being too many stars. At some point, when we were studying the universe, we had the Milky Way, and it was the spiral galaxy like a pancake. It was like a disk. And then all of the local cosmologists like Sam and Ella had to come in and make it harder because they added more stars. And they were like, okay, now you have your satellite galaxies and you have your globular clusters. And also the Milky Way is not flat, it's twisted. Also, there are tidal streams now. But let's zoom in on this picture a bit just to get to where the Small Magellanic Cloud is in this diagram. To remember a sense of scale, I said for it to be a white dwarf, it has to be 4,000 light years away. The Milky Way by radius is about 40 kilolight years across. The Small Magellanic Cloud is about 200 kilolight years away. It is quite impossible for a star, if it's in the Small Magellanic Cloud, moving with the Small Magellanic Cloud, to also be a white dwarf. So coincidence? I think not. So clues so far. It's blue, it's hot, it looks like it's in the SMC, it moves like it's in the SMC, it's probably a duck. I mean in the SMC. So it can't be a white dwarf and be in the SMC. The Gaia machine classifier is probably wrong. So the question becomes, what is it? Well, we can get more clues by looking at other surveys. This is the 2 micron all sky survey that looks in the infrared, which is light that is redder than visible red light. Then this is the low resolution version of what Gaia saw. In this version, it's a single pixel. My computer could not handle the higher resolution image. This is what it looks like with the European Southern Observatory, which is ground-based. This is what Hubble saw. And this is what the Newton Space Telescope saw. And what's interesting is this, I showed you infrared, I showed you visible light, which is what we can see with our own eyes. And then this is UV. And what's interesting is in UV, this star is brighter than any other color. So we have so here are clues again. We know it's blue and hot, it's in the SMC. And we know that it's UV bright and infrared dim. So we have more color information than before. And if you're wondering where I was able to look up all these other surveys, astronomers have done actually a very good job of data management. We've kind of assigned okay, yeah, I see your head, Sam. We've assigned all the stars a system of coordinates, and we've assigned them basically a telephone number that we can look up in a database. So it's basically like Google, but for stars. So I was able to Google the star in something called Simbad, which is Google for stars. And I was able to find all the information about it, including that there was a paper in 2019 that gave it this classification. To break this down, the B over here is from Jump Cannon system, where it just means it's a B star, it's hot, it's blue. The 0.2 is you can break each of those letters down from 0 through 9, meaning how hot is it within that category. So 0 being very hot and 9 being cold, or cool. So B0 means a very hot B star, and all this little V means is it's part of the main sequence on the HR diagram. So Gaia thought white dwarf down there. This paper from 2019 thinks it's a hot blue star up here. And then when we look at all the colors all together, including the ultraviolet, what we realize So white dwarf, 99% probability, hot blue star on the main sequence. Our star is over there, once we account for UV. So the machine classifier is wrong. The first pass from humans in their big paper was wrong. They weren't specifically trying to classify this star, they were classifying a bunch of stars, so it was like a first pass classification. And our star is neither. So what is it? First, before that, here's the scientific version of the HR diagram. Again, blue going that way, bright going that way. This is where, this is being generous. It's giving you B0, B0.5, B1, B2. So all being very generous with what kind of B star it could be. And this star is both bluer than a B star would be, and it's dimmer than the B stars would be. So it's something else entirely. So we have all these clues. We know that it's not. We also know it's too big to be a white dwarf, too small to be main sequence. What is it? We can kind of have to go and stake out the star. So what we did is we looked at 10 years of photometric data of a telescope pointing at the star and measuring its brightness every night. We found that it was dipping every so often. So basically, we figured out how often it's dipping, and then we stacked every one of those periods. It's about a 4-day period over 10 years, and we get this light curve that's folded. So it's a folded light curve, and you can kind of see a little dip over here and a bigger dip over here. And what that looks like is what you would get from a binary star. So the simplest explanation to our mystery is that our star is not alone. It has an accomplice. And what's even stranger is this binary star isn't just in a binary. It's a binary which underwent mass transfer. So we think that this star probably evolved a little bit. It got a little bit cooler. It started fused a lot of its hydrogen into helium. So it started to build up a helium core. And then its partner stripped off all of the hydrogen surrounding it, leaving an exposed helium star. This is called the stripped star binary. So you started out with 2 stars. One evolved slightly more. The other one sucked off its envelope, and you're left with one helium star that has no hydrogen envelope left, and one star that has gained mass. So again, what are the clues that it would be? What would we expect if this was a strip star? We would expect it to be helium-rich and hydrogen-poor when we look at its spectra. We would expect the spectrum to be blended, so we would expect to see light both from the main sequence star that did the stripping and the stripped star. We would expect it to be blue-hot, and it correctly matches how blue the star we're looking at is. We'd expect it to be small and compact, which matches probably partially explains why Gaia misclassified it. And the range of luminosity fits our stars as well. So it's actually a very good fit. So I mentioned spectroscopy at the beginning of the talk, and Chekhov's gun, so spectroscopy is coming back. And we have a few different lines. So Balmer lines are what astronomers call the series of hydrogen lines. So, and what's really unfortunate with spectroscopy is that hydrogen lines and helium lines tend to be basically in the same place. They're almost impossible to distinguish. So they're kind of these blended lines, so it's really hard because we wouldn't know whether it's coming from the stripped star or from the main sequence star. So the stripped star spectrum is up here with all the little dips. The main sequence star is down here with all the little dips. And then you have this, these would overlap, these would overlap, and then you have one line over here that's like, this line would only come from the stripped star. So that would be one smoking gun. The biggest smoking gun is actually these nitrogen lines over here because those only can come from a the stripped star. So if we were to see in the composite spectra, we happen to see these nitrogen lines, we would be dead sure that this was coming from a stripped star binary. There are a couple other lines where we would know like that we would expect to come, but those are the biggest ones. The last comment I have, well, sorry, not the last comment, I have more comments. One more comment that I have is on size, and why I made a big deal about size being important is when I'm talking about strip stars, I specifically mean a very specific mass range of stars. I mean stars that started out their lives between 8 and 20 solar masses, so 8 to 20 times the size of the sun, mass of the sun, and post binary interaction are at between 2 to 8 times the mass of the sun. And the reason I say that is there are stars that are small that behave with similar photometry and sometimes similar color called subdwarfs that also exist, but they don't quite have the same formation mechanism always, so we're going to ignore them. And there are other stars that are much bigger and much more energetic, and there's a special type of O stars called Wolf-Rayet stars, where they can do this stripping by themselves. They just are energetic enough that they can blow away their hydrogen envelope by themselves. They don't need help from a binary companion. So when I'm talking about this binary formation mechanism, I'm being very specific about what size of star I'm talking about. And that's also helpful because the size of star, I mentioned that luminosity comes from size. The other thing that comes from size is surface gravity. And something that surface gravity affects is how broad your absorption lines in your spectra are. So these are spectra of different helium stars. In the black in the middle are what we would expect a strip star to look like. Up here in the top are different Wolf-Rayets. As you can see, Wolf-Rayets have a lot of have some lines facing the other way. They're lines that are emitting rather than absorbing. So they're excited elements that are giving off light, not just eating it up. And you kind of have these giant vertical lines, and those are very telltale for Wolf-Rayets. Strip stars don't have those. And for subdwarfs, you might notice that it's very subtle here, but the lines are slightly broader. They're smaller stars, they're more compact, so that causes the lines to be broader. And then when we get to white dwarfs, which are these bottom two spectra on this panel, the lines are very broad. That's kind of the final nail in the coffin for the Gaia machine classifier. It's definitely not a white dwarf. The spectra we're looking at, ended up seeing, was nowhere near this broad. So Gaia is definitely wrong. The humans were a little bit closer. They were wrong about it being main sequence. It's more likely than not a strip star binary. And the reason we kind of found it in the first place is kind of the conceit of this talk is I gave it backwards. We didn't find this star because someone was looking through 2 billion Gaia objects and saw one of the classifications was wrong. We didn't find it because someone was going through the tens of thousands of astronomy papers and saw that one of them got like one star wrong. We found it because we theoretically predicted that this type of star should exist, and we went looking for them. This work started at the University of Toronto, where they started to look through archival UV photometry to try to find stars that had more UV light than optical light, or visible light. In 2023, they found 16 candidates. This work one of their scientists moved up to Caillou Leuven, where I'm studying, and have now built up that catalog to be over 100. So we now have over 100 of these candidates for this object. And then finally, we still need high-res spectroscopy and multi-epoch photometry, the kind of photometry where we're studying a star night after night for years on end to be able to better understand these objects. Why should you care about the stars? So here is a little animation about all the supernovas we have seen in the history of humanity. I think Rubin is expected to see something like 10,000 supernova per year. Someone who works on Rubin can double check me on that. But we're going to have order or two of magnitude increase in the number of supernova we see every year. And this is how many we're already seeing. The amount of weird objects that you see, if it's 1 in 100, and you're only observing 1,000 stars, you're probably going to find 10 of them. If you're observing 10 billion stars, that probability of finding weird objects jumps up. So in terms of binaries alone, and this is where I kind of disagree with the trivia, 70% of massive stars have binary interactions in their lifetime. And this statistic comes from stars that are born as O stars. 70% of them have binary interactions. And then 30% of those massive stars, experience some kind of mass transfer or envelope stripping of that type. This contributes to strip stars contribute to multiple fields of astronomy. If you care about gravity waves, these are gravity wave progenitors. If you care about why some galaxies tend to be UV bright, this is one possible contributing factor or explanation. If you care about the reionization, what are some explanations for the reionization of the universe, and you care about like Big Bang cosmology, strip stars, you care about strip stars. If you, like me, care about finding weird supernovas that go bump in the night, like hydrogen poor supernova progenitors, supernovas, these might be progenitors for those kinds of events. Quickly to recap, before Sam throws me out, Gaia, to summarize the talk today, Gaia said that this star had to be a white dwarf. Humans first pass said it had to be a main sequence B star. I spelled star was wrong. I don't know how I did that. Astrometry showed our star was in the Small Magellanic Cloud. Photometry showed it was too bright to be both in the Small Magellanic Cloud and be a white dwarf. Photometry then showed it's too dim and blue to be main sequence. Both the suspicious UV excess and the dip in the light curve point to it being a stripped star binary. Spectra confirms everything. That's currently where we're at with this project. We're working on the spectra to confirm and publish the result about whether or not this star is indeed a stripped star binary. Conclusion, stars can be characterized by color and their temperature, by their size, brightness, and mass, by their chemical composition. There are too many stars to do this all by hand. There are also too many stars in general. Astronomers increasingly must use machine learning to classify stars, but it's not perfect. When looking for stellar weirdos, we can use several different tools and clues to know what we're looking at. Binaries are a key part of understanding our universe. Binaries are cool, and strip stars are very hot. Thank you. Are there any questions?
Don't forget to repeat the question.
Yes. Yes. Oh, for binary systems, it's a whole range. It depends on how much mass each of the stars has. For this type of system, order of days is typical. But for binaries in general, it can range to even years. There are some binaries. Oh, right. Thank you. The question was, the system has a 4-day period. Is that typical for binaries? And the answer for binaries is no. Binaries can range from periods on the order of hours to on the order of decades. For this type of system, however, we do think it's on the order of days. That's a great question.
Since finding an eclipsing binary requires that the eclipse is between the host star and us, how many do you think are out there where you don't
For strip star binaries, for this mass range, that one. So far. The question was, sorry, I'm bad at this as well. The question was eclipsing the light curve I showed. Where did I put the clicker? I don't know what I did, Sam.
Not there.
This light curve that I showed is a particular type of light curve called a eclipsing binary, where the binary is going in front of each other. So you could have it the other way, where the binaries are circling each other, but neither is passing in front of the other one, so you'd never see that dip. So the question was how many of these objects are in eclipsing binaries, and of the order 100 that candidates we've identified so far, only one, the one I showed you, or one I've been talking about, is in an eclipsing binary. Yes.
In that situation, do you see the stars move in the sky, especially in that circular one? Would you see the star move a little bit?
That's a great question. So the question is, would we see the stars move in the sky? Yes, it depends. Not for this one. That's kind of it's far away enough, and the binary is close enough that the light getting blended is kind of the entire problem. But there are binaries where you can visibly see both the binary companions, and you can see them move around each other with just through photographs. There are other things where you could see a Doppler shift in the spectra. There are other ones where you would see the dip like this. So there are different ways of detecting binaries. But the answer is yes, sometimes. Hey, thank you, everyone.
These chairs are so hard to get out of. Thank you.
Yeah.
All right, sorry about that. Thank you all so much for coming to Astronomy on Tap number 109. Give another round of applause to our speakers. Great work. As always, our next Astronomy on Tap is next month on August 19th. We will be back here in Stoop Ballard to enjoy the rest of our summer months. As always, I've been your host, Sam. It's been a pleasure. Have a nice night and get home safely. And also, if you won trivia, make sure to get a prize. Excuse me, sorry.